What's up, you guys? So, as promised, this is the standard error video. If you haven't watched the standard deviation video first, go back and watch that. But this will discuss an extension of standard deviation called standard error. And standard error is used in statistics as a kind of full way to look at how good your data is. So standard deviation, if you recall from the last video, says how spread out the data is, right? So if you have an average, but the data points that you use to get that average are pretty spread out, you're going to have a high standard deviation. Whereas if the data points that you use to get that average were pretty close to the average, you're going to have a low standard deviation. But on top of that, one thing that makes your data good is the number of data points you have. So if you have, let's say, an average of 10, right, and your data points are 10.5 and 9.5, yes, those would have a pretty low standard deviation because they're not too far away from the average, but we don't have tons of data points. So standard error is a full picture look at your data and how good it is. So the equation for standard error, and again, I apologize for the glare. For some reason, this part of the board gets a lot of glare. But the standard error of the mean is the standard deviation, which tells you how spread out your data is, over your sample size squared. So if you think about this, it's actually pretty clever because this will tell you how spread out your data is. If you have a low standard deviation, which means your data isn't spread out that much from the average, you'll have a low standard error. And furthermore, if your sample size is bigger, that means that you're going to have an even lower standard error. So if you have like 10 data points versus 2 data points, the 10 data points is going to lower the standard error more. And you want a small standard error from the mean. So good data has a low standard deviation and a high sample size, which would mean that there's not a whole lot of standard error from the mean. And whereas bad data would have high standard deviation, so it's pretty spread out, and on top of that there's a low sample size, so maybe only 2 data points. And that would give us a pretty high standard error of the mean. So let's just look at this with an example. So let's say we have 2 data sets. We have data set 1 and data set 2. And let's say you want to make the claim that a particular fertilizer helps a plant grow to, or let's say you want to make a claim that a specific species of plant grows, if given the ideal conditions, will grow to about 10 centimeters. So let's say this is your hypothetical data set 1. This would be good data because you have not only a lot of points, but the points are not very spread out from that average. So you making that claim that the average height of a plant is about 10 centimeters, and that's about where the plant is going to grow if given ideal conditions, this would be good data to support that. Whereas this would be bad data. So yes, it gives you the same average, but here you only have 2 data points. That's not a very convincing argument with only 2 data points. And on top of that, the data points are pretty spread apart. So you saying that it's going to grow about 10 centimeters given ideal conditions actually is not a good claim with this data. So if you were to calculate the average, it's 10 centimeters for both. So if you looked at them on a graph, they would both read 10 centimeters. But the standard deviation of this, if you were to calculate it, now I used Excel to calculate this. I wouldn't recommend actually calculating this out by hand. When we're dealing with a lot of data, sometimes it's better just to use a program like Excel. But the standard deviation here is 0.527. And the standard deviation for data set 2 is 5.66. So just looking at the standard deviation without even having looked at this data, you can tell that this data, data set 1, is a lot less spread out. So if you look at this, the average is 10. They don't deviate from 10 centimeters that much. So our standard deviation is pretty low. And then for here, our 2 data points deviate from 10 centimeters quite a bit. So our standard deviation is 5.66. Now, let's further take this and decide on the standard error between the 2 data sets. So for data set 1, the standard error of the mean is equal to the standard deviation over the square root of the data set, so, or your sample size. So your standard error of the mean is 0.527 standard deviation for data set 1 over 10 data points that we got. So if we got the standard error of the mean, it's roughly 0.167. So that is not a that's not a relatively large standard error. Whereas here, if we did the standard error of data set 2 with our 2 points that were pretty spread apart, our standard deviation is higher, and our sample size is lower, so we have 2 and 5.66, so naturally our standard error of the mean is going to be higher. It's going to be 4, as opposed to 0.167, or about that much. So if we looked at them side by side on a graph, and we looked with, or we plotted them with error bars, you would see data set 1 and data set 2 have the same average, but data set 1, the error bars are a lot smaller, and data set 2, the error bars are a lot bigger. So here, I would be more inclined to trust this data with smaller error bars than this data, because this has a smaller standard error of the mean. So hopefully that was helpful, and throughout the year we'll be looking at different problems that deal with standard deviation and standard error, and hopefully you guys will become good at it before the AP exam.